Our next presenter is Mike Buchanan from Sapelco Sigma Aldridge, who will talk about trap selection, fast GC and troubleshooting strategy for purge and trap GC volatiles. After earning his Bachelor of Science degree in biology from Edinburgh University of Pennsylvania in 1988, Mike spent 12 years working as an analytical chemist and supervisor in environmental laboratories. Mike joined Sapelco Sigma Aldridge in 2000 as a technical service chemist, providing real-world, hands-on knowledge to customers, particularly in the areas of purge and trap volatiles, GCMS of semi-volatiles, US EPA extraction methodologies, and NIOSH OSHA methodologies. In 2005, Mike moved into the marketing group as product manager for gas separations, assuming responsibility for the worldwide marketing of GC columns and accessories, gas purification and management products, and bulk adsorbents. And so without further ado, I'll turn the presentation over to Mike Buchanan. Mike?
Thank you very much, David. As David mentioned, we will talk about purge and trap volatiles today. A brief section will discuss on the adsorbents that are used. We'll go through some trap selection. A brief section on fast GC techniques. We'll spend some time on troubleshooting, and we'll end with a summary. The common adsorbents used in purge and trap include carbon, 10X, and silica gel. The carbon adsorbents, namely Carbopac, Carbotrap, Carboxin, Carbosiv, and activated charcoal, trap analytes based on the analyte size and shape. 10X, which is a porous polymer, also traps analytes based on the analyte size and shape. The silica gel is a little bit different in that it will trap the analytes based on the polarity of the analyte. Each of these three adsorbents has specific advantages and drawbacks, which we will discuss. Before we discuss the drawbacks and the advantages, let's discuss a bit about what a particle looks like and also the pores in the particle. In particular, the pores are very important to particles because the composition of those pores determines the absorption and desorption characteristics of that adsorbent. As you can see in the diagram, we have a particle with macropores, which are fairly wide, down to micropores, which obviously are the more narrow pores. Mesopores tend to be a little bit in between those two. Specialty carbon is nice because we can engineer those pores with more or less of any pore type to serve a specific purpose. The pores can be through pores or closed pores, which influences the micropore strength. In this diagram, we show the micropore being a through pore, meaning it goes all the way through the particle, comes out the other side. A closed pore would be closed at the back end, it would be a dead end. And again, that will influence the micropore strength. We can also engineer those pores to be tapered, nice like the diagram from a macropore tapering down into a mesopore, and then eventually down tapering to a micropore. And that will greatly influence the thermodynamic efficiency, both getting analytes trapped and also having analytes desorb back off the trap. So without further ado, we'll go into the three types of adsorbents. Carbon, the main advantage of, or one of the main advantages of a carbon is its high desorption temperature of 250 degrees Celsius. What that allows is a rapid transfer of analytes to the GC. Gives you much less band broadening and also improved chromatography, especially for the gases. Also, during the bake step, we can use that higher temperature to do a better job of removing large compounds that are stuck in the pores. Carbons are relatively hydrophobic in nature, which means less water is getting trapped and therefore getting pushed over to the GC. Carbons can also be dry purged. This will help to remove any residual moisture from the system. And as we mentioned on a previous slide, carbons, we can engineer the pore composition, therefore we can make carbons very application specific. The drawback of using a carbon, especially the stronger carbon adsorbents, the carboxins and the carbosivs, is they tend to have a great efficiency for methanol. Methanol may do one of two things. Methanol may get into the trap and fill the pores during the purge mode, especially the micropores region, leaving no space available for the gases. So So when the gases come along during the purge mode, there's no room left in the micropores. They blow off the back of the trap again during the purge mode. The second thing that may happen is the gases may actually get trapped, again, during the purge mode in those micropores, but methanol will come along, being slightly smaller in diameter, will actually wiggle its way into the micropores and kick or displace the gases off the trap, or out of the micropores. Therefore, the gases will get displaced during the purge mode, and they'll blow off the back of the trap. Now, the methanol doesn't stick around. The methanol during the desorb mode will be pushed off the trap. You'll get a big methanol peak in the chromatography. The methanol will get out of the trap. The trap will be ready for the next run, ready to go. However, that run will have very low response for the gases. There is a solution, and that is to keep the total amount of methanol in your sample, standards and blanks, less than 50 microliters. In fact, less than 20 microliters is even more desirable. 10X also has a high desorption temperature, 250 degrees Celsius. So again, limiting the band broadening and also being able to use a high temperature during the bake step are the two advantages that we get from 10X. 10X is a great adsorbent with the ability to trap analytes with a wide range of sizes and shapes, as small as pentane and as larger than the trichlorobenzenes. 10X is well studied. There's lots of breakthrough volume for numerous analytes. 10X is also referenced in many methods. There's numerous literature about 10X. It's also easily to obtain. The drawback of 10X is that it's not suitable for the gases or any other small molecules. You must use a bed behind 10X to grab the small molecules, including the gases. The other drawback of 10X is we can have oxidation of the polymer framework, can produce high background levels as residual monomers that are left in the adsorbent are released. These will be detected as aromatic ring compounds in the chromatography. In extreme cases, voids can be created, leading to some channeling. And as the picture shows, 10X is a porous polymer based on 2,6-diphenylene oxide. Silica gel, unlike carbon and 10X, analytes are predominantly trapped based on analyte polarity instead of analyte shape and size. So it's a little bit different than both the carbon and the 10X in that regard. But what that allows is a great affinity for polar analytes, especially the ketones, that are very water soluble and may not trap well on other adsorbents. Silica gel is also referenced in many methods in numerous literature and also easily obtainable. Two main drawbacks with silica gel is it has a lower desorption temperature, 180 degrees Celsius. So using a trap that has silica gel in it must desorb at a lower temperature. You will have a little more band broadening, and also during the bake step, you will not be able to bake the trap nearly as high. And the second main drawback is its affinity for moisture. This causes more moisture to be trapped on the trap. Eventually will be pushed over to the GC during the desorb mode. And because of its great affinity for moisture, you cannot dry purge a trap with silica gel in it. You'll also remove all those polar analytes will come off with the water. That was, again, a real quick review of adsorbents. We want to talk about the different traps. And regardless of what absorbents you're using in your traps, there is some logic to how you build a trap. And there's a specific order you want to put the beds in, again, regardless of what absorbent you're using. You want to build the trap, or the trap manufacturers build the traps, that the sample will come into contact with the weakest adsorbent first and the strongest adsorbent last, in the purge mode. So we want the larger compounds to trap on the first bed. The smaller compounds will pass through those first bed or two, and they'll trap on the stronger beds later. If you have the trap in reverse order, or you have a weaker bed not present in the trap, you have just strong beds, the larger compounds will get trapped onto those stronger absorbents, and they'll become irreversibly retained. So think about it like a sieve system, as the diagram or as the picture shows. Traps work very similar to a sieve system. Weaker at the top, stronger in the back. And we get asked quite often which trap is best. And that's kind of a difficult question to ask because there is no absolute best trap for all situations. They're really application specific. It really depends on what method is being followed, in particular the list of analytes that need to be detected. Also, whether it is desirable to trap the small analytes, the gases, and that kind of goes to the first point. What are the list of analytes that you need? And secondly, the hardware being used. Is a moisture management system being used? Is it being bypassed? If it is being used, is it functioning properly? And in that regard, we need to talk a little bit about handling moisture. Water is a problem for volatile analysis. It chromatographically interferes with the gases. In extreme cases, over time, moisture will damage the quadrupoles in the GCMS systems. There are two strategies for dealing with water. One is a dry purge. And a 1 to 2 minute dry purge will remove water to an acceptable level without losing any absorbed analytes. In extreme cases, a 4 to 5 minute dry purge will remove virtually all water, but you'll also lose some absorbed analytes. So again, we recommend keep your dry purge to 1 to 2 minutes. Longer than that, yeah, you'll remove more water, but you're also going to lose some of your analytes. So 1 to 2 minutes is appropriate for a dry purge. Second option is using a moisture management system on the concentrator itself. This is a section of tubing, a specially coated section, which will grab the moisture as it passes through, and then it will eventually bypass that and vent that from the system. You must maintain the moisture management system so it has the proper operation. And a couple of notes. If you have a trap with silica gel, as we mentioned earlier, you cannot dry purge that. And a second note is we do not recommend using a dry purge and moisture management system at the same time. One or the other is really what we recommend. So I have 5 slides here which are going to show different traps that we recommend for the different configurations and different methods. So for most methods that are out there, if you're using a dry purge and you have the moisture management system off or not available, the traps that we recommend are the K-trap or the I-trap. The K-trap is the most popular trap. It is able to absorb and deabsorb small analytes like the gases to some of the less volatile analytes, particularly 1,3,5-dichlorobenzene. The I-trap is also another good trap. It has a 4th bed in addition to the 3 beds in the K-trap. The 4th bed is a Carbopac C, which goes in front. It's actually a weaker material than any of the beds in the K-trap. So that will help protect the beds behind that, and it gives you more efficient adsorption, desorption of the larger analytes. In the little diagram here, we show our traps from A to M, and the different color schemes. The different color schemes, the absorbent key in the top right corner show that. So the K-trap starts with a Carbopac B, then it has a Carboxy 1000, and ends with 1 centimeter of our Carboxy 1001. The I-trap is similar, but it has 7.6 centimeters of a Carbopac C in front of it. Another configuration for doing most methods is using moisture management and having a dry purge not available, or not using a dry purge. So this would be the other way of doing most methods with moisture management, no dry purge. The C-trap or number 10 trap are really what I would consider the best choices for these methods. These are great traps as long as the moisture is being managed by the concentrator. Both traps are very similar. There's a combination of a 10X polymer, which will grab most of the large analytes, anything larger than, let's say, a pentane. So it grabs the halocarbons, will grab your BTEX. Silica gel bed will grab the polar analytes, in particular the ketones. And both traps have a carbon bed at the very end to grab your small analytes like your gases. The C trap uses an activated charcoal. The number 10 trap uses a slightly stronger carbon material. The K or the I trap will also work, and it really depends on the system you're using and how you want to set that up. For doing medium-level soil methods, this is where you might be able to dedicate a system if you have a large project coming through with a lot of medium-level soils. If you can dedicate an instrument, I recommend doing either an E-trap or a D-trap. And what this is with a medium-level soil is typically you do a soil extract with methanol, and then you spike 10 or 100 microliters of that methanol extract into 5 milliliters of water. This amount of methanol is not a problem for the E or the D trap. The drawbacks is you will have a lower desorption temperature of 180 degrees Celsius because we do have a silica gel bed in there. So your peaks will not be as sharp. You'll have a little bit more moisture being transferred to the GC. If that moisture is too much of an issue, the D trap may be the better choice because it does not have the silica gel bed. Both the K and the I trap will work if you cannot dedicate an instrument for medium-level soils. I would recommend either the K or the I. Again, depends on how large the project is, how many instruments are available. Again, if you can dedicate an instrument, that would be recommended. Same thing with the very popular BTEX only methods. And again, if you can dedicate an instrument for doing just BTEX samples, the J trap was specifically designed for BTEX. And as you can look at the diagram there, it's a very small bed length in the traps, just two absorbents, a very small section of Carbopac C, and then a 1.2 centimeter section of Carboxy 1001. It's really only designed to grab BTEX and analytes about that same size. It will not absorb the small compounds, which will allow you to have a shorter analytical run. So the small gases, pentane, things of that nature will not absorb, so you can actually start your oven temperature much higher because you will not have those small analytes to have to deal with. So again, if you have a whole lot of BTEX only method or samples coming through, dedicating an instrument, you can get much quicker sample throughput using the J trap. But again, if you cannot dedicate an instrument, the K or the I trap will also work for doing BTEX. And something else that has been popular for a while is BTEX plus MTBE, or what's known as gasoline range or organic methods. This is really looking at gas spills for doing these leaking underground storage tanks methods and such. The M or the L traps were good for that. Very, very similar to the J trap. It just has a longer bed. It's a second bed, and it's a Carbopac B bed. Again, methanol in the gases will not be trapped, so you can use a quicker analytical run. But these traps have a little bit longer and a little bit stronger second bed than the J trap, so it will grab analytes down as low as MTBE or as low as pentane. If you need to grab pentane, the M trap's what we recommend. If you do not need to see pentane, the L trap will give you a little bit quicker run time. And again, in a pinch, the K or the I trap will work for both of these also. So that gives you an idea on trap selection, and we have a few minutes we'll spend on fast GC for volatiles. The principles of fast GC are decreasing analysis time by using a shorter column, quicker ramp rate, a higher velocity of your carrier gas. Those changes will give you quicker, but you'll also decrease resolution. We don't want to lose any quality, so we'll offset that decrease in resolution by using a narrow ID column. We'll switch to hydrogen carrier gas where we can, and we'll use a low film thickness as we decrease the narrow ID or decrease the column ID. And really, fast GC is manipulating a number of column and instrument parameters, providing a faster analysis times while maintaining the resolution. And this is an example of a conventional GC run for volatiles, 30 meters in length, 0.25 millimeter ID column, 1.4 micron film thickness, using a 30-to-1 split. We have a 17-minute run of the 38 analytes, which isn't too bad, but we have a pretty poor response for the gases, and this is probably typically what many labs would see in their laboratories and their analysis. It's acceptable. The gases are just harder to get good peak shapes for, and many labs will probably run with this. Switching to fast GC, we're obviously going to, as we mentioned, shorten the column to a 20-meter column. We're going to decrease the column ID from a 0.25 to a 0.18. The film thickness will go from 1.4 microns to 1 micron, and we kept the split the same. We've increased the run, the oven ramp rate a little bit, so we're running faster. We're 9.5 minutes as opposed to 17, but we're still not real happy with the resolution of the gases. I think even some of the response for peak 3 and 4 actually even got worse. And so we're doing fast GC, but we didn't adjust enough of the parameters, which is a common mistake, and we can do better than this. And by just changing that split to 100-to-1 split, we get a much better resolution and response for the gases. So now we're at a 9-minute run, just almost the same as the previous run, but the peak shapes and the separation of everything looks fantastic, and much improved responses in peak shapes for the gases. And it's a common mistake to not increase the split enough when switching to the narrow ID column. So those 3 runs we just did, the parameters that we changed were the desorption, and that's not something you control at the instrument, but by increasing the split, it automatically increases the desorb flow rate. So when we went on that 3rd run to the 100-to-1 split, it automatically kicked in a much faster desorption flow rate to 150 mils per minute. And that's actually what gives us the much better response and peak shape for the gases. Obviously, the fast GC, as we mentioned, a shorter column, a narrow ID column, and most other parameters are very consistent. The ramp rate a little bit faster for the fast GC than the non. And as you'll see, we did stay with helium for all of our runs. One of the fast GC principles was going to hydrogen when applicable, but a lot of the mass spec methods, you must stay with helium. In this case, we did. And a question we get asked all the time also is by increasing the split ratio, do I tend to lose sensitivity? And the answer to that is no. We tend to maintain sensitivity because we get a much better signal-to-noise ratio when we generate such narrow, sharp peaks. And these are the conditions that stayed the same for all 3 of the runs. And this is the list of the peak IDs for all 3 of those runs. Another question we get asked is, now that I have a run that's less than 10 minutes, how do I take advantage of that? Because the purge time and the desorb time, the bake time, takes longer than that. 2 options for doing that is the dry purge time and the bake time parameters are usually not controlled by the method. So we can use a ballistic dry purge and bake with a couple different instruments manufactured after several different models that can use extreme fast and hot dry purge and bake times. Another option is to use 2 concentrators per GC while one analysis is running, and in the bake mode, the second system, the second concentrator, if you will, is in the purge mode. So one sample is always ready for the instrument when the instrument is ready. So there are ways that you can drastically increase your throughput with a fast run and different concentrator options for doing that. And then our last section we'll talk about is troubleshooting. And before we get into a strategy for this, some of the best practices that we feel for purge and trap is documentation, by far number 1. Use a maintenance logbook. Record everything as you change it, no matter what it is, when it was done, why it was done, did it fix the problem, and this is just your preventive maintenance, changing liners, changing seals, clipping columns, whatnot. By doing a well-documented maintenance program, it may save you weeks of troubleshooting in the long run. Secondly is to make only one change at a time. This will really allow you to uncover the root cause of the problem. And secondly, if you make 2 changes, the problem may not have fixed because the changes may have offset each other. One might have fixed it, one might have made it worse. You make it both at the same time, it looks like nothing happened, and really it might have. So again, one change at a time is really key for there. And then something else that we recommend, keeping what we call a good trap. Remove and store a trap that was working when it was removed as a reference for when issues occur at a later time. And with that trap, replace the caps, place the original shipping container, label it properly, and put it in a drawer and protect it from vibration. Vibration on a trap over time will actually start to loosen the bed. So we want to keep a good trap, stored properly. And you'll see the use of that good trap as we go through the troubleshooting flow. And so whenever we have a problem, and this is a strategy that our technical service group has used to help many customers over many years, is to go back and install that good trap. That was a trap that was working when it removed. You've stored it properly. So reinstall that good trap. So we're going to try to eliminate where the problem is, and we're going to evaluate the system with a standard or whatever it is you're running. And we're going to say, is that system now working? And so we'll go to the left. Yes, the system is now working. The next step is now to take what we call that good trap out and reinstall the trap that you had just taken out at the beginning of troubleshooting. So the trap that wasn't working a few minutes ago. So we're going to reinstall that trap, and we're going to evaluate the system again with a standard. And then we're going to evaluate, is it working? If it's working now, it's probably a moisture issue. In the next slide, we'll talk about what the moisture issue is. If it's not working now, it probably was a bad trap. And we'll talk about that here in 2 slides or so. So back at the top at the flow, if we installed that good trap and it's not working, the next question asked is, did any operating parameter get changed? And if it did, you might have an incorrect parameter. If it was not changed, you probably have a system issue. And we'll talk about troubleshooting both of those techniques in these upcoming slides. So potential cause moisture issue. This is where we put the good trap in, it worked. We put the trap that wasn't working and now it is working. Leads us to believe you have a moisture issue somewhere in your system. This is caused because as samples are purged, moisture is carried into the concentrator. And if you have any active sites or cold spots, moisture will accumulate. It could be in the trap, could be somewhere else, could be in a valve, could be a grain of sand that's stuck somewhere in a valve. Anywhere that there's something that's not a smooth surface, moisture will accumulate. And this will cause low or no response of the more water-soluble analytes. Also, it's commonly seen as your internal standard responses decrease throughout the tune window. So you may start your 12-hour window, you may have your internal standards, and they will drop steadily over time to a point where they're no longer acceptable. You come in the next day, you shoot your blank, you shoot your standard. The internal standard response is back up where it should be, but throughout the day it tends to drop. That's an indicator of a moisture issue somewhere. When you open the system, it allows that moisture to escape. And removing a trap vents all that moisture. Also, when the system sits idle at night, the moisture tends to dissipate. That's why the next day, the moisture or the internal standard response is good the next morning. So every day or every night when the system sits idle, it dissipates, or when you open the system to the room, the moisture tends to dissipate. So when we did in the troubleshooting flow, we opened the system twice. We put the good trap in, and we also put the trap before troubleshooting back in. So we actually vented the system twice. So if the response will come back after opening the system or letting it dissipate overnight, after letting the moisture dissipate for a night, you have a moisture issue. You have a cold spot. You have an active site somewhere in the system, or if you're using moisture management, it's no longer functioning properly. So that's where you want to focus on finding that grain of sand, finding that cold spot, finding a heat trace that is no longer working properly or has been moved. So again, going back to the flow, we did the troubleshooting. We put the good trap in, it worked. We put the old trap back in, it is still not working. You have a trap issue, and one of the solutions is just to simply call the trap manufacturer and request a replacement. But if you're in a pinch and you have to run samples this night, you don't have a spare trap, or you're up against hold times, you need that trap to work, you can try an elevated bake out. And there's a couple of scenarios with this, or a couple of considerations. Is you must take the PTFA ferrule, if you have one, you must take that off and use a vest full of graphite ferrule that can withstand 400 degrees Celsius or higher. So once we have that Teflon or PTFA removed and a good vest full of graphite ferrule on there, we're going to bake the trap at 40 mils per minute with helium, 375 degrees Celsius for 4 hours. After 4 hours, we're going to let everything cool down. We're going to discard that ferrule that we put on there, because at that temperature it's going to be pretty well masked, and we're going to replace it with a new ferrule, whatever we normally use, and then we're going to evaluate its performance. And a lot of times that will bring a trap back to life if it was a bad trap. What that does is that extreme temperature will help get things out of the pores that are stuck, any of the heavy analytes that are where they should not be, and it will allow you to recover that trap. Another note, this procedure can only be used with carbon traps, such as the HI, JK, L, or M. These traps can easily handle this temperature. We don't publish this. We publish 250 as the maximum temperature for the carbon traps because most people tend to use a PTFE or Teflon ferrule, and their maximum temperature is 300. And we don't want to be responsible for any melted PTFE stuck in instruments. So you need to verify the instrument can handle that temperature. I believe most of the concentrators can. But again, if you really are in a pinch and need to recover a trap, this is something that works pretty well. So going back to our flow, we reinstalled where we put in that good trap to start our troubleshooting. And it did not work, and one of the parameters did get changed. We're not sure we had the parameter set right to begin with. Is probably an incorrect parameter. We'll discuss that here. There are a lot of combinations of auto samplers, concentrators, how you have your inlet set up to your GC, comm dimensions, detector combinations. It's quite a large list. It's impossible to list here what every individual parameter should be. It's really going to depend on the hardware being used. At this point, if you're not sure what your parameters, your operating conditions should be, we recommend contacting one of the technical services and having a complete list of all your parameters handy. In 2 slides, I'll show you a list of a nice form you can fill out and send it into one of the technical service, list everything that you need for them. There are many concentrator manufacturers listed alphabetically there. There are several trap manufacturers. You can contact the manufacturer of the entire system, the instrument companies, and also MDL is a third-party vendor, and they do a really good job with some of the troubleshooting too. It's a pay-as-you-go service, but they're actually really good. And we'll talk more about parameters here in the next slide. But in this slide, if you diagnose it as a system issue that you did not make any changes, so something's just wrong, it's not the trap, it's not moisture, you don't have an incorrect parameter, something inside the system has broke. A valves went bad, the comm's going bad, something else is wrong. This is a way to help narrow where that is. And it's a systematic procedure for identifying where that is. And so we recommend making 2 standards, one at 50 and one at 200 nanograms per microliter with all your internals and surrogates in methanol, and we're going to perform the series of 5 runs. So we're going to inject half a microliter of the higher concentrator standard directly into the GC. And that's if it's acceptable. I prefer, particularly for the troubleshooting purposes, I prefer when we hook up a purge and trap to a GC that we actually plumb the transfer line into the carrier gas, leaving the injection port available to do an injection with a syringe through the septum. That's the way I prefer to do it, just so that we can do this troubleshooting down the road. Commonly, people will actually run their transfer line and butt connect it right into the column, either above the injection port or into the injection port. which eliminates your ability to inject into the GC. So you might not be able to do this first injection. It depends on how you've configured your injection port. But if you can inject in the top of the GC, do this injection. This will check that the GC is operating properly. The second injection is 2 microliters of the lower concentration standard into the top of the trap. Now, the top of the trap isn't always physically up. It's not always the top of the trap. Top of the trap means the inlet during the purge mode. So it's where the gas goes in when the system is set to purge. We call that the top of the trap. It's where the weaker adsorbent sits. It's also when you're in the desorb mode, where the gas comes from. It's the outlet in the desorb mode. So if you can identify the top of the trap, you're going to inject 2 microliters right into the top of the trap, and then you're going to immediately step it to desorb preheat. What this will do is it'll just check your tubing and the valving from the trap to the GC and beyond. It will not go in, none of the gas or none of the this injection will actually make it into the trap material itself. So we're going to check your tubing and your plumbing and your valving from the trap to the GC. Injection 3 is, again, 2 microliters of the weaker standard. We're going to do the same thing, inject into the top of the trap. We're going to dry purge that for 5 minutes. That'll force those analytes into the trap, into the adsorbents, and then we're going to step that to desorb preheat. This is now checking the trap material itself, as well as all the tubing and plumbing to the GC. Injection 4 is to do 2 microliters of the lower concentration standard into 5 mils of water and set it up manually on the concentrator. Don't use your auto sampler. This is going to check your tubing and your plumbing and your valving from the auto sampler, or from the concentrator rather, through the system. And then step 5 is to do a normal setup on the auto sampler and let the auto sampler run through it. And what you'll see is the response for all 5 of these runs when you compare them. And where you see a drastic loss of response will help indicate where the issue resides. Is it a particular valve? Is it the 64-port valve? Is it the 8-port valve? Is it a specific length of tubing? Is it the trap? Is it the auto sampler? And this will help you focus additional troubleshooting into that area. So again, you want to divide and conquer is what we call this. Find out where in the system the problem is, and then we can concentrate on there. Slide or 2 ago, we talked about instrument conditions and stuff. This troubleshooting worksheet, it's Sapelco T596001. You can obtain it from our technical service, but it lists all the questions of all the different parameters that you would use with purge and trap, whether it's GC or GCMS. Works for any trap, any sample, concentrators, whether you're using moisture reduction, whether you're using dry purge, your GC conditions. And if you were to get this form, fill it out, and send it into any of the technical services, they would be able to help walk you through whether your parameters are correct or incorrect. So quick summary, we recommend selecting the proper trap for the application. Again, if you can dedicate an instrument or system for some of those other methods like the medium level soils or BTEX, that'll allow you to get faster throughput. If not, the K-trap will work for most applications. Employ fast GC to increase throughput. It's well worth the time taking the method development, taking the week or so and setting that up will give you much, much faster throughput. And also we recommend using a sound troubleshooting strategy. To learn more about purge and trap and our other environmental solutions, our website, sigmaaldridge.com/environmental, lists everything for organics, metals, wet chemistry, sample collection, a whole lot of chromatograms, and some newsletters. This is the Sapelco site located in Belfont, USA. The Fluke site where we make some of the standards and solvents is located in Switzerland. And thank you for your time.
Well, thank you, Mike, for that excellent presentation. We now have time for a few questions received via the Q&A box. And for those of you listening who have questions, now would be a very good time to send them in. So, Mike, the first question we have is, if I cannot dedicate a system for medium-level soils using an E-trap, what trap do you recommend?
Again, the K-trap is a good all-around trap. The I-trap also makes a good choice. And again, it really depends on how big the project is, whether you want to dedicate a system. But again, if you absolutely have one instrument or a lot of mixed samples coming through, some medium, some not, the K or the iTrap both work great for that.
Okay, thanks, Mike. The next question is, for fast GC, will sensitivity decrease when the split ratio is increased?
As long as it's within reason, no, the sensitivity won't decrease. If you switch from a 30-to-1 split to an 800-to-1 split, yeah, I would expect some sensitivity decrease. But in the example we showed, we increased the split from 30-to-1 to 100-to-1, and we see no decrease in response because we're generating such sharp, narrow peaks. We have a much greater signal-to-noise ratio. The sensitivity doesn't drop whatsoever within reason. Again, an excessive split ratio increase would cause a decreased sensitivity, but 30-to-1 to 100-to-1 is not excessive split increase, so no.
Okay, and Mike, I think the last question we have today is, where can I find additional chromatograms with instrument conditions?
Okay, for not only just the volatiles, but for all of our environmental, at that website I showed, sigmaaldridge.com/environmental, there's a section there on chromatograms. We'll list all of our chromatograms for environmental, and I don't know how many we have on volatiles, but it's well over a dozen or so.
Well, Mike, once again, thank you very much for your presentation today. And if any other questions do come in, I'm sure that Mike would be happy to respond to them via email afterwards.